Recording in progress.
Okay. More receiver stuff. A little bit about dynamic range, intermods, third order intercept, which you have to think about a little bit, but it's actually not that complicated. I can't say that. Pre-selection sensitivity and link margin. In link margin, it's math. You have to add and subtract. Blocking dynamic range is, I guess, a very big deal in receivers. So it's a measure how strong a interfering signal has to be to reduce the strength of an incoming signal by 1 dB. Fortunately, I have a little chart that helps explain that. So they say the range is the difference in dB between the noise floor and the level of the incoming signal that causes that 1 dB gain compression. So if we look at the chart, if everything was perfect, you see this straight line that goes up. Okay. In an imperfect world, we can't follow the straight line. So at some point, we start to be nonlinear and deviate. So what they're saying is, at what point does the output from the signal become 1 dB less than the input? So if you've got, as you increase the signal level, so we went from 0 to whatever this was, up 10 dB, but the output only went up to 9 dB. So it was 1 dB less on the output. So that was 1 dB of basic compression or blocking. And that's how they define the blocking dynamic range, what the signal level was in order to create that 1 dB compression. Clear as a bell? Well, we'll see. What is meant by the blocking dynamic range of a receiver? Let's see.
Yeah, I think that's what I'm staff to memorize too. Especially around.
Well, look at what you can throw out. This one, right? And this is not third order harmonics. So we just have to pick between alpha and Charlie. And Charlie doesn't say anything about a 1 dB compression. So it must be alpha. It's kind of hard to understand at first. Once you understand it, then it makes sense. Intermodulation. So we can have unwanted signals that are generated by a mixture of two other signals. If there's some nonlinear device. And one of the examples they always use is a rusty bolt. Because the iron oxide can actually act as a mixer. So if there's RF signals around, it can cause or third order intermodulation, creates some and different signals and can re-radiate, and you can actually pick them up. So apparently rusty bolts on an antenna tower can create that. Obviously, it's got to be where there's a fairly strong RF signal, or it's not going to go very far. But anything out there, any nonlinear type device that could act as a mixer can cause this problem. And then they talk about the third order intercept is kind of like the blocking thing. And it's going to be another chart. So it'll warp your mind even more. So we say that the third order intercept, in this case, say it's 40 dBm, means that if you have two signals that are 40 dBm, you're going to get a third order intermodulation product, third signal, at the same level as the input signals. So when they get up to 40, this third order product is going to be up to 40 because it increases at a faster rate. At 3 dB for every 1 dB of input. So it's basically 3 times the rate or twice the rate. So the higher that number is, the better your receiver. So if you're looking and comparing radios, the one with the highest third order intercept is a better receiver than the other one as far as third order intermodulation. So what causes intermodulation in an electronic circuit?
Difficult one to say. Try.
Did I double tap or is that? Oh, I did. Well, you knew it anyway, right?
Of course.
Yeah.
All right. This one is just showing what intermodulation is. So we have two signals, omega 1 and omega 2, and they're coming into this nonlinear amplifier. That's why it's got that kind of curved line through it. And what we get out of it are intermodulation products. And these you need to kind of remember that it's going to be 2 times omega 1 minus omega 2 and 2 times omega 2 minus omega 1. So you take each of those two input frequencies, you multiply one of them by 2 and subtract the other one frequency. And then you do the opposite. You multiply the other one by 2 and subtract the other frequency from it. And that'll give you the intermodulation products. And the reason that it's important is there's a test question where you have to figure that out.
Well, there's always a test question. Yeah. First of all,
And then this bottom one is kind of showing where this one is in the bad place. So this one in this case, we're using F1 and F2 instead of omega. So you got two different frequencies. And you can see the two F1 minus F2 and the two F2 minus F1 products. And then you're going to, those would be the third order. And they turn out to be the closest ones to the original frequencies. The second order IMDs are much farther away. And the third order harmonics are much farther away. So it's only the third order intermodulation products that are close. And the second order intermods are farther away. So these are the only ones we care about with the 2F1 minus F2, 2F2 minus F1. So those are the two things you need to remember. Or you just guess. What does a third order intercept level of 40 dB mean with respect to receiver performance? Vanessa? Charlie? Why are odd order intermodulation products created within a receiver of particular interest compared to other products? No. Yeah, when they say odd, really, they're talking about the third order.
Yeah. Okay.
They're going to be the closest ones, and they may be within the passband. Desensitization. If you have a strong signal, okay, that's not what you want to listen to, it can reduce the sensitivity of your receiver. And they call that desensitization. Almost got that one right. But it can also be caused by poor dynamic range. So you have the blocking or compression. It's like desensitization. And you also can start to get some spurious signals because you got some cross modulation going on and all that good stuff. So they recommend that you decrease the bandwidth of the receiver in order to reduce it. And once again, you really want to have your passband of the receiver as small as possible and still be able to receive the signal that you want to receive. So what is the term for the reduction in receiver sensitivity caused by a strong signal near the received frequency? Yep. Which of the following describes problems caused by poor dynamic range in a receiver? Sounds good to me. Which of the following reduces the likelihood of receiver desensitization?
Noise coming in.
Let's see. Attenuator.
And it's kind of intuitive, right? You don't want to attenuate the signal, right? Why would you want to do that? It's crazy, but obviously the unwanted signals, you gotta get out of there.
Yeah, sometimes you get too much signal.
Sure. Too much.
Pre-selectors. So you can basically narrow the passband on the front end so that you can filter out signals that are outside of the band you want to listen to. So what's the purpose of the preselector in the communications receiver?
Sure.
Charlie. Oh, here we go. My favorite question. Uh, this is kind of an example of what we just talked about a few slides back on the intermodulation distortion. And this example, they're showing that you have your receiver tuned to 146.7, and you got another station that's at 146.52. So it says you might hear signals on 146.34 and 146.61, as well as the station you're listening to, which is 146.7. And that happens because of these intermodulation products. So if you remember the 2 times minus stuff we just talked about, so you take 2 times, well, whether that's F1 or F2, minus the other signal, and you come out with 146.7. If you do 2 times the other one minus that one, you also come out with 146.7, which means you would hear both of those intermodulations. I don't know if the question is still in there where you actually have to figure that out. It was a tough one. What creates intermodulation interference between 2 repeaters in close proximity? Well, we can eliminate what?
Sandy.
Right. Has nothing to do with it. So is it caused by feedback? Okay. So must be Bravo, right? Because the final amplifier can be a nonlinear device. So if it has any nonlinearity, it will cause some of these intermodulation products. Oh yeah, here it is. What transmitter frequencies would cause an intermodulation product signal in a receiver tuned to 146.7 when a nearby station transmits on 146.52? You can either memorize this answer or figure out how to work it.
Oh, no, that's. It's alpha. And you know, this is another one that you should, you take the F2, 2 F1, and you come up with all kinds of stuff. But I think that the trick is you end up with a frequency that's the difference between the 2 signals
Right.
below. So that would give you your 146.
They made it more difficult than just simple F2 minus 2 times F2 minus F, the other one.
And then the other one splits it.
Because you actually have to do some algebra. Because you have a different unknown. And you have to solve it to come out with their 2 answers. That's probably the hardest one in the whole extra. But it's, you know, it's fairly simple algebra, just addition and subtraction and knowing how to manipulate equations. A properly terminated circulator at the output of the transmitter may reduce or eliminate intermodulation interference in a repeater caused by another transmitter close by. What the circulator does is basically a filter, usually a cavity type filter, that if I understand it right, never actually having done one, allows you to direct the received signal and the transmitted signal through the same antenna, even though they're on different frequencies. Because on a repeater, you're copying the input signal to the output frequency on the same antenna at the same time. So it allows the input to come in and the output to go out without the output getting fed back into the input of the repeater. So it has to have a lot of separation, I guess, between the two frequency signal wise. So it's essentially a 3-port device where one of the ports is the antenna and the other two are the input and output of the repeater. So which of the following is used to reduce or eliminate intermodulation interference in a repeater caused by a nearby transmitter? Okay, link margin. This is one of the things that really becomes important on trying to do something like Earth, Moon, Earth, where that link is what you do is you add up all the losses in the system and then subtract those from the gain or the power of the system, and the net result is the link margin. So you look at what your minimum signal is that you can receive with your receiver, and then the power coming in and all the losses, and that difference is the margin that you have. So you want to have probably at least 2 or 3 dB margin, because things vary a little bit. Propagation won't be the same. So what is the link margin in a system with the transmit power level of 10 watts or 40 dBm, a system antenna gain of 10 dBi, a cable loss of 3 dB, a path loss of 136 dB, a receiver minimum discernible signal of minus 103 dBm, and a required signal to noise ratio of 6 dB. Should be.
Well, it's either 8 or 14.
8 or 14?
It's one of those two. For sure.
Plus or minus.
It's not so hard.
So on this one, I think for both of these questions on here, if you take the transmit power and your antenna gain, you subtract everything else,
Right.
and you're gonna come out right here.
You should. Once you make sure the dBms and the dBs and the dBis are straight. So we had 40 and 10. And we subtract the 3, the 136, the path loss. We have to add the minimum discernible signal on the receiver as a positive.
So if you subtract the negatives, positive.
Yeah, so that was my question, you guys on what's negative, but if you minus negative, you're adding X.
Because the 10 watts and the antenna gain are positive, and the receiver signal is basically positive. So everything else, all those other losses have to be subtracted from those. What is the received signal level with the transmit power of 10 watts or 40 dBm, transmit antenna gain of 6 dBi, a receive antenna gain of 3 dBi, and a path loss of 100 dB? So just different numbers, same problem. You're right. Wow. That was easy.